So, good evening, everybody. So let's go for uh, next part of Hilbert space, the notation of Dirac notation. So let's try to understand what we are going to do. So in last class, we have discussed all the notation of Hilbert space in form of function, but today we will just trying to use a different notation, and that will be the Dirac notation. So I hope last class I have discussed how we are taking kit and anything. So if any function and that is belongs to Hilbert space, that can be written as a kit. And if we are talking about complex conjugate of phi x, then this will be treated as bra. What is meaning of kit? Meaning of kit is actually equivalent to column vector. Mathematically, column vector. And bra is all about row vector. What is meaning of that? If I am writing phi kit as a column vector, let's say this is C1, C2, C3, then the phi bra will be C1 star, C2 star, C3 star. You will just take the complex conjugate of this and column will be converted into bra. And similarly, if please mute yourself. Please mute yourself. Okay. So suppose we are taking phi bra or some, let's say another vector, let's say chi bra, and this will be, let's say A1, A2, A3. Then the kit part is written as a column vector, and this will be A1 star, A2 star, A3 star. So these are the thing. So there is correspondence between column and row vector. Now, what we are going to do? So everything, if you are writing that, you can just replace this thing as a notation wise kit and bra. And now if I am writing a scalar product, what is the scalar product? The scalar product written as phi and psi, and this is mathematically equivalent to minus infinity plus infinity phi star, let's say function of x, psi will also function of x, dx, and this must be some finite number. And the same thing in bracket notation, I can write phi psi. So these are the same thing. If I am writing the whole this particular thing, or I am writing this thing is nothing but scalar product. So it's a very interesting notation. It's a very interesting notation that you can use into the quantum mechanics. But there are some limitations. What are limitations? You cannot write phi kit, psi kit. You cannot write. This is void. Void means they are not accepted. So you cannot write phi kit, psi kit. So, but when you can write, when they belongs to same space, same vector space. When belongs to same vector space or same Hilbert space, you can say they belongs to same Hilbert space, then you can, the kit and kit, bra and bra is not allowed. But when they belongs to different vector space, suppose one will belong to, and you can have analogy also, this type of analogy. Suppose you are doing the partial differential equation. How you are writing the partial differential equation? You are writing psi x and y. You can write, let's say, x as a function of x, y as a function of y. So then you can directly multiply two function, because both are belongs to different space. One is belong to x, another is belongs to y. So similarly, I can write, if I can have psi x and y as a kit, we can write this thing as, let's say, x as a x, and that is direct product y as a function of y. In vector, this is known as direct product. So y, the scalar product is also known as inner product. So they are also known as inner product. So this is the notation of inner product, and which is also physically it will physically tell you scalar product. So what we can do, we can just redefine each and every concept we have written as a vector form also. So obviously they will follow the linear vector addition, a scalar vector addition, they are the same thing. So we will just try to write what will the orthogonal, orthonormal, and all this kind of situation. So let's try to write each and every. So this is the revision of same thing whatever I have done into the last class. We are just going to revise it in form of ket and bra. If you have any doubt right now, you can just ask me.
So can you explain the last one?
Which
Psi
one?
x
Last
y.
one? I don't remember what is last one. Inner product.
Psi
This one?
inner product.
Inner
Inner
product
product.
is same as a scalar product. You can name this. Mathematician is usually tell it inner product. Okay.
Okay.
That if you are writing some row vector a1, a2, a3, and let's say b1, b2, b3. This is known as what? Inner product. Okay.
Okay.
So these are number. Inner product are always number. They are number. Scalar number. In quantum mechanics, it can be real, it can be imaginary. Don't worry. So let's try to go for quickly for all different thing we have just done into the last classes. So obviously, how you can go for? You can go for vector addition. So you can write psi plus phi is equal to chi. So if this belongs to vector space, this belongs to same vector space, this will belong to same vector space. Closure, you can write psi phi plus chi. Sorry, you can go for commutation. So that is phi plus psi. This is commutation. You can go for psi plus phi plus chi, or you can write psi phi plus chi. These are very trivial. So I am just writing it so that your notes can be compiled. Then you have 0 psi plus minus psi is equal to 0 vector. And or you can write psi plus 0 vector is equal to psi. Sometime you can put 0 ket also, sometime you cannot put 0 ket. And then you can just go for the scalar multiplication. That's a very interesting. A plus B psi can be written as A psi plus B psi. A psi plus phi can be written as A psi plus A phi. you can go A B psi can be written as B A psi. 0 to psi ket is equal to always 0. These all are trivials. So this is, I think, these gone into your DNA. So you can just easily write each and everything. But main thing is all about scalar product. So obviously the scalar product is defined as phi psi. These are the scalar product. And now this is basically known as, and these are the number. And now what is the orthogonal condition? That phi I, phi j is equal to delta ij is orthonormal. So in the orthonormal, you have orthogonal also as well as normal also. What is meaning of that? Is equal to 1 if I is equal to j, if is equal to 0 if I is not equal to j. So they are orthonormal condition. Now look at the most important thing. Why I have written this thing? Look at, we will just try to understand from the different perspective. There are some confusion, and let's try to remove this confusion, and this is very important. Let's try to go for this. Look at,
सर राइट नहीं किया था
राइट नहीं किया था तो बताया क्यों
स्केलर
नहीं?
प्रोडक्ट से नीचे सर
phi I, phi j is equal to delta ij. ठीक है? And this will be 1 if I is equal to j, if equal to 0, if I is not equal to j. ठीक है? Now look at here. Look at, this is very interesting. Suppose I have written psi as C1 phi 1 plus C2 phi 2. This is very interesting. This is very interesting. What will be psi star? The psi star will be just C1 phi 1 plus C2 phi 2 whole star, which will equal to C1 star phi 1 star plus C2 star phi 2 star. And now these are functions. So if I am writing mod psi square is equal to psi star psi, then we can write this is C1 star phi 1 star plus C2 star phi 2 star into C1 phi 1 plus C2 phi 2. I can just write this thing. So how many terms we have? We have actually mod C1 square, mod phi 1 square, mod phi 1, this into this, plus mod C2 square, mod phi 2 square. Now you can write this thing as C1 star C2 phi 1 star phi 2, the cross term, this and this. Then you have C2 star C1 phi 2 star phi 1. Are you getting it? So this is equivalent to mod psi square. So this is what? This is a function. Now let's go for, if I am writing same thing something like, and this is a huge confusion between the students. So if I will write psi as C1 phi1 kit plus C2 phi2 kit, and what will be psi bra? Psi bra is equal to C1 star phi1 plus C2 star phi2. And if I am writing psi and psi, then you have C1 star C1, that is number, mod C1 square phi1 phi1 plus mod C2 square phi2 phi2 plus cross term C1 star phi1, sorry, C1 star C2 phi1 phi2 plus C2 star C1 phi2 phi1. Now anybody tell me that is that this one and this one are the same thing or different thing?
Same.
That is the actual problem. So what is this thing? This thing is the number. But what is this thing? This thing is not number. This thing is function. Probability अभी नहीं बात करेंगे, अभी जस्ट मैं फंक्शन कह रहा हूं, जब तक postulates में नहीं आएंगे सब बात नहीं करेंगे. So this thing is just function. So obviously this thing is not equivalent to this thing. Please, when this thing and this thing are equivalent, then you will write this whole thing as, suppose I am writing psi star psi dx minus infinity to plus infinity, that will be mod C1 square. This can be written phi1 star phi1 dx minus infinity to plus infinity plus mod C2 square, that will be phi2 star phi2 dx minus infinity to plus infinity, and then we will just go for cross term C1 star C2 minus infinity to plus infinity phi1 star phi2 dx plus C2 star C1 minus infinity to plus infinity phi2 star phi1 dx. Now you can see this is equivalent to this one. What is meaning of that? What is actual meaning of that? The actual meaning of that, this is actually psi and psi. What is actual meaning of that? This is actually, I am writing, this is actually phi1 phi1. What is meaning of that? This is actually phi2 phi2. And similarly, you can write this thing as phi1 phi2 and this thing as phi2 phi1. So you have to be very careful when you are using the Dirac notation. You have to be very careful when you are using this particular Dirac notation, because most of the people doing this type of blunder. So whenever you are talking about the mod psi square, then only functional form of vectors are useful. Then Dirac notation is not useful at that time. So what you have to do, you have to convert your Dirac notation as a function, and then you can go for this. Yes, someone have till this is something like probability density. So yes, when we will go for the postulates, keep in mind that bracket is a scalar product, but mod psi square is not a scalar product. Mod psi square is actually psi star psi, and that is function. So please keep in mind that psi psi is not equal to psi star psi, please. So if you have any doubt, you can just ask me. Okay, so let's try to go for some problem based on this Dirac notation and whatever we have done, orthogonality and all kind of thing, and then we will go for the operators. Okay, so let's try to go for some basic problem. Okay,
Sir,
now yes.
can you please tell again when we should use Dirac notation and when I just missed that part?
No, no, you will use Dirac notation always. But when you have to go for mod psi square kind of situation, when you have to go for probability density mod psi square, then you have to go for functional form, because you cannot write psi psi as psi star psi. Okay, these two are not same, these two are different. Are you getting this thing? So this is most important. So once you will go to the problems, you can understand when you have to use this. So right now I am just giving you warning that don't directly use all this thing. Okay, so suppose someone will give you that psi 1 is given by c1 phi 1 plus c2 phi 2, and psi 2, or let's say it is a1 a2, let's say it is a1 and it is a2. And what is psi 2? Psi 2 is b1 phi 1 plus b2 phi 2. It is also given that phi I phi j is delta ij. What is meaning of that? Meaning of that, phi I phi j are orthonormal. They are just orthonormal. Now what is question? Find the condition find the condition such that are orthonormal. Are orthonormal. Okay, so we have to find the condition such that they are orthonormal. So what we have to do? How many condition you have to get from here? How many condition? 1, 2, 3. How many condition?
3.
3 condition. Very good. What are the condition? First condition is the normalization of psi 1. Second condition is the normalization of psi 2. And what? And condition is the orthogonality. So if this is my psi 1, then obviously the bra part of psi 1 is equal to a1 star phi 1 plus a2 star phi 2. And what we have to do? We have to take the multiplication psi 1 psi 1 must be equal to 1. So this is nothing but what? A scalar product. This is nothing but what? A scalar product. So how you have to write it? You have to, scalar product means you have to just go for psi 1. So we have to just, I'm just using here. So this will be just psi 1 must be equal to 1. So how many terms will be there? 4 term will be there. Bra and kit. So what will be first term? The first term is A1 star A1 phi 1 phi 1 plus second term is A1 star A2 phi 1 phi 2 plus A2 star A1 phi 2 phi 1 plus A2 star A2 phi 2 must be 1. Now, what is this particular value? What is this
One.
particular value? This
One.
is
1.
1. What is this particular value? 0.
0.
What is this particular value? 0.
0.
What is this particular value? 1.
1.
And what is this thing?
Mod A1 square.
Mod A1 square. So this is actually mod A1 square plus mod A2 square must be equal to 1. And similarly, from the second part, you will get, what will be second part? Mod B1 square plus mod B2 square is equal to 1. And now, last but not the least, what are these? So these are the normalization condition. What is this? This is basically normalization for psi 1. This is normalization for psi 2. And now we have to go for what? Orthogonal condition. So what are the orthogonal condition? So we have to go for orthogonal condition. So you can have two equation, but both will give you same answer because right side we have 0. So what you can write? You can write something as so what you can do, you can just go for psi 1 psi 2. I can write this thing also. This will equal to what? 0. What is meaning of that? You have to write psi 1 psi 2 is equal to 0. So how you will go for this? Psi 1 is, so this is bra. So we will use bra and we will use psi 2 for ket. So first term is A1 star B1 phi 1 phi 1. Second term is A1 star B2 phi 1 phi 2. Third term is A2 star B1 phi 2 phi 1. And last but not the least, that will be A2 star B2 phi 2 phi 2. Then again, what will be the condition? The condition that this must be equal to 1, this must be equal to 0, this must be equal to 0, this must be equal to 1. So what will be the condition? The condition is A1 star B1 plus A2 star B2 must be 0. Some people can get answer B1 star A1, B2 star A2 is equal to 0. Both are the same thing. If you are using the complex basics of this thing. So this is condition for orthogonality. So this will tell you about the orthogonality. Okay. So if you have any doubt, you can just ask me. These all are very basic, very trivial, very trivial. So, but we have to just recap all this thing because when time come, you can do it very fastly. Now you can directly write, okay, phi 1, phi 1 is normal, phi 1, phi 2 is orthogonal, so it will be 0. So you can directly use this kind of concept and we can directly write. But first time you have to do each and every step point by point. Okay? Okay. So let's come to next very interesting thing, that is linear independency. And this is one of the most important concept used into quantum mechanics. So let's go for linear independency. Now, what is meaning of linear independency? Means one vector cannot be represented in a linear combination of another vectors. So they are basically known as what? Linear independent vectors. So how you will check whether vectors are linear independent or not? So what we have, let's say we have phi 1, phi 2, up to we have phi n. So we have to check whether these vectors are linearly independent or not. So what will happen? You will make an equation, and that equation is C1 phi 1 plus C2 phi 2 plus C3 phi 3 up to Cn phi n is equal to 0. So this is actually equal to 0. And how many solution you can have? In general, you can have infinite number of solution for C1, C2, C3 because you have only one equation and n number of variables, then you have possibility of infinite number of solution. But for linearly independency, there exists a unique solution. C1 is equal to C2 is equal to C3. All Cn must be equal to 0. So if this condition exists, then you can find the linear independent vectors. The linear independent vectors. So this will be all about linear independency. For example, you can take phi 1 as 1, 0. You can take phi 2 at 0, 1. We have to check whether they are linearly independent or not. So obviously there are two vectors. So you will check C1 phi 1 plus C2 phi 2 is equal to 0. And you can make an equation that is C1 1, 0 plus C2 0, 1 is equal to 0. And if you are going to solve this equation, then what you will get? You will get C1 is equal to 0, C2 is equal to 0. So easily you can get. So what is meaning of that? Meaning of that phi 1, phi 2 are linearly independent. Why you are using linear independent? Because once you will get the linear independent vectors, you can write any vector into that space in a basis of linear independent vector. What I am saying, very simple thing, don't worry. You can write 2, 3 vector as a 2, 1, 0 plus 3, 0, 1. Means you can write a vector as a 2 time, and let's say this is phi 1 or let's say this is psi. So I am using psi is 2 times phi 1 plus 3 times phi 2. So once you will get the linear independence vector, you can get the basis vector actually. What you can get? You can get the basis vector. So once you will get the linear independent vector, you can write any vector into that space in a basis of that one. You can have various example of this in Euclidean space. For example, two-dimensional space. Suppose this is I cap, this is j cap. You can write any vector into this two-dimensional space, any vector into this two-dimensional space in a basis of I and j. Why you can write it in a basis of I and j? Because they are linearly independent. But in a quantum mechanics or in general in a vector sense, I want or we want the basis vector must be orthogonal in nature. So this is one of the very interesting thing. What are the interesting thing? That so up to this, if you have any doubt, you can just ask me. Then I will go for next explanation.
Sir, could you explain once again that C1 and ket pi 1 this thing?
Where is the problem? I cannot repeat the thing. Sorry.
This one, this C1 and ket pi 1 plus C2 ket pi
So
2.
what is problem here? I have written the equation.
This, yeah, this C1 and C1 equal to C2 equal to 0 you mentioned here, right? I didn't get actually.
That is the, yeah, come on. If this condition hold, then phi 1, phi 2, phi 3 is linear independent. Are you getting this?
Yes, sir.
Come on.
Yes, sir.
Okay. So just look at from the example. I am just checking phi 1 and phi 2 are linear independent or not. I am making an equation something like that, and I have get C1 is equal to 0, C2 is equal to 0. They are linear independent.
Okay.
Okay?
Okay.
Okay. Just focus on class. Just focus on very nicely, because we are at the very prime level, primarily level actually. Not prime level, primarily level. So this time we are just learning or revising the definition. Lot of things have to come. Okay. Now, what I am going to say, let's go for the another example. Let's say phi 1 is equal to 1 1 and phi 2 is equal to 1, or let's say that is 1 0. So let's check whether they are linearly independent or not. So we have C1 phi 1 plus C2 phi 2 is equal to 0. So I have make an equation because I have to check only for two vectors. And now we can write C1 1 1 plus C2 1 0 must be equal to 0. And from here you have C1 plus C2 is equal to 0, and C1 must be equal to 0. So why C2 is equal to 0? So yes, these vectors are also linearly independent. Now look at what I have done. First vector I have taken, the first example I have taken 1 0. I saw why I have taken two-dimensional vectors, because they are in a plane. So this is 1 0 and this is 0 1. In the second problem, what I have taken this vector, that is 1 1. So you can find 1 0 and 0 1 is also linear independent, and 1 1 and 1 0 are also linear independent. But you can find these two vectors are orthogonal, but these two vectors are not orthogonal. So there is a very interesting observation, and you can prove it also, but I am not going to prove. What is the observation? Every orthogonal vector are linear independent but every linear independent vector are not orthogonal. So orthogonality will serve the two purpose. Linear independency will serve only one purpose, that it is only linear independent. It may be orthogonal, it may be not orthogonal. But if vectors are orthogonal, then it must be always linear independent. So if you are getting the orthogonal vectors, then what you will get? You will get also linear independent vectors. And normalization is the very simple thing. You can normalize any vector with the normalization condition. So why in a quantum mechanics, what we choose? We always choose a orthonormal basis, because orthonormal vector are okay, orthonormal, they just behave like a perpendicular vector, as well as they are linearly independent such that they can make a basis. What is meaning of basis? Any vector can represent in a basis of linear independent vector, or if vectors are linear independent, you can make a basis. But in quantum mechanics, which type of basis we needed? Mainly the orthogonal basis. So what you will do? You will always try to find which kind of vectors? They are basically orthogonal vectors. And obviously normalize you can do, so you will always find the orthonormal vectors. So we will just find orthonormal vector. Why? It will be 100% linear independent. It will 100% linear independent. So up to that, if you have any doubt, you can ask me. Then we will go for next example. Okay. Now we have done is this thing into column vectors or this thing. We can also do it in term of function also. So, and look at how you can explain this thing is a very wizard kind of thing. Let us assume phi x is equal to e to the power minus x square. I am putting x is between minus infinity to plus infinity. And psi x is equal to x e to the power minus x square. Again, I am using minus infinity to plus infinity. We can check they are orthogonal or not. So what is orthogonality? You can just write phi psi must be 0. So this is the orthogonal condition. So what you can do? You can just go for phi star psi dx, obviously from minus infinity to plus infinity. And when you are going for this, you can just go for phi star is e to the power minus x square. And x is the real function. So this is x e to the power minus x square dx minus infinity to plus infinity. This must be equal to what? 0. Because these are odd function. These are odd function. This will be 0. So yes, phi x, phi and psi are orthogonal vector. Then it must be linear independent. It must be linear independent. So let's check. So what you can get? C1. So you can just write C1 phi 1, C2 phi 2 is equal to 0. You have C1 e to the power minus x square C2 x e to the power minus x square must be equal to 0. You can take e to the power minus x square common. C1 plus x C2 is equal to 0. This is not equal to 0. So you have C1 plus x C2 is equal to 0. So what is the value of C1 and C2? If this is something like a polynomial and it is right side 0, what is value of C1 and C2?
0.
0. 100% they are 0, isn't it? Because you will equate the coefficient. What you will write? 0 into x to the power 0 plus 0 into x to the power 1, and then you can equate the coefficient on both sides. You will get C1 is equal to 0 and C2 is equal to 0. So obviously they are linearly independent also. And it have to be linearly independent because they are orthogonal. Now, look at the thing. This is most a wizard kind of thing. So, are you getting all this thing? I am just plotting this to curve. If we are able to plot this to curve, plot is very simple. This is Gaussian curve. So this will be something like this. And this will be something like this. So this is phi x versus x. And this is psi x versus x. Now you can believe that these two functions are orthogonal in nature. Means if you will take the projection of this function onto that, if you can assume this is one my direction, this may be treated as another direction, and both direction is actually orthogonal in nature because their scalar product is 0. How you can justify this thing physically? It is next to impossible to justify what is happening here. But yes, mathematically you can see, yes, if the scalar product is 0, you can easily call it as a orthogonal vector. So don't try to mug up unnecessary what is physical meaning of it, what is physical meaning, okay, aisa hoga. No, this kind of situation cannot be happen. Everything you have to verify with mathematics. Our brains are not so developed in terms of visualization that how we can visualize these two things as orthogonal vectors. Something one is this direction, another is this direction. But we can treat them as directions because we have this mathematics. So this is a wonderful techniques of the mathematics of the Hilbert space that you can go for this. Now we can go for one more problem. So this is very interesting. So are you getting this? So should we go for next one? Okay. Suppose we have any function psi x. Let's say this psi x is a, where x is between -1 to +1 and 0 otherwise. Let's say another function phi x is equal to bx plus c. Again x is between -1 to +1 and 0 otherwise. Find the value of a, b and c such that psi x and phi x are orthonormal. Same type of question we have done in form of kit, but now same type we are doing in form of this thing. A and B is real number. You can take these are real. Okay. So A, B, C are real. So first psi is equal to 1. Psi is equal to 1. So you have to just go for minus infinity to plus infinity. Psi star psi dx is equal to 1. But if you will take the integration, then what you will get? This is equivalent to minus 1 to 1 a dx is equal to 1. So you can just use this thing, a is equal to 1 by root 2. So we can get a is equal to 1 by root 2. Second equation, we can go phi x psi x is equal to 0. This is orthogonal equation. So what you can write, or psi x, phi x, whatever you could. So they are A, B, C are real. So you can just go for minus infinity plus infinity phi star x psi x dx is equal to 0. So obviously psi x is equal to a is 1 by, so we will go for integration minus 1 to 1. Phi x is bx plus c, and this will be 1 by root 2 dx is equal to 0. So now from this equation, how you can get this particular value? Minus 1 to plus 1 bx dx 1 by root 2 plus 1 by root 2 c dx minus 1 to 1 is equal to 0. This is 0 due to odd function. So here c must be equal to 0. So you can get c must be equal to 0. Just do the integration and c will be just come out, and that will be 0. This is odd function, so this will be 0. So c will be 0. Then we can go for the orthogonality, sorry, normalization condition of phi x. So when we will go for the normalization condition of phi x, then what you have? You have phi x, sorry, phi x is equal to 1, and you will just go for minus infinity to plus infinity phi star phi dx, and that will be mod b square minus 1 or b square because it is real x dx is equal to 1. So b is equal to, I think, root 2 upon 3. Isn't it? Am I correct? Sorry, x square. This will be x square, b square, x square. So b is equal to root 2 by 3 because you will take phi star phi. Yes.
Sir, why we have not written bx plus c star instead of
Because c is equal to 0, I have gotten 0.
no, sir, just before one step before.
Why?
Phi is bx plus c. So phi star is
Here or here?
here, sir. Yes, sir. Yeah.
Here.
Yes,
Here
sir.
I have written bx plus c. What is problem?
Sir, if phi star we need to write here.
Phi star is okay. So this is phi star, na? Phi star bx plus, you can, I have just told before that b and c are real number. So there is not any need to do go the star. Okay.
And sir, how
Okay.
this minus 1 to 1 bx dx will become 0?
Because it is odd function. It is very simple. Any odd function minus a to plus a is equal to 0. Just you can do it with yourself. Okay. And this is the simplest integration. And anyway, that will be 0. Now look at the physics or basic thing. What we have get? We have two function, and look at this function. I can construct, you can do calculation with yourself. Don't worry. The calculation is very simple. So why I have taken this example. Just look at what is psi x. Psi x is 1 upon root 2. And what is phi x? Phi x we are getting root 2 upon 3x. And now you can see these two functions. Suppose I am plotting psi x versus x, then psi x is equal to some straight line between -1 to +1. So this will -1 to +1, -1 to +1. Otherwise it is 0. And phi x is a straight line passing through origin. And this is from -1 to +1. So this is phi x. This is from -1 to +1. It is not going there. So this is up to this. This is also up to this. You can use these two functions as orthogonal vectors. How you will visualize, it's your problem. But yes, we can use these two functions as orthogonal vectors. This is very interesting. And these two are a straight line, don't worry. Have you seen this type of function in your mathematical physics?
Yes, sir.
Have you done polynomials?
Yes, sir.
Have you done polynomials?
And the
Have you done Legendre polynomials?
Yes, sir.
Yes,
Yes, I do.
So what is P0 and what is P1?
P0 is 1
One
and
is
P1
One
is
is
X.
X. Something like this, isn't it? Yes or no?
Yes, sir.
Yes,
P0 is 1, that is a straight line, and P1 is X, that is this thing. Look at. So now I am giving you the example of Hilbert space. What are the examples of Hilbert space? Can anybody give me answer? I have given you hint. So I think I have to just in the last minute of this class. What are the examples of Hilbert space?
Orthogonal polynomials.
All polynomials. All polynomials in some form can be treated as a Hilbert space. And now you can go to revise the polynomials. And you can find there is orthonormal relationship for each polynomial. Have you seen? It is different issue that there is some weight function is there. For example, in Hermite polynomial, if I am correct, you have something this type of equation -x square hnx hmx is equal to delta nm kind of situation. If you have revised your equation, you can have this kind of situation, isn't it? So this is the weight function, and this weight function we introduce into our quantum mechanics, as well as we will also introduce in our quantum mechanics. Anyway, that is different issue. So what are the examples of Hilbert space? Polynomials with their weight function, obviously. Now, what are the practical examples of Hilbert space? Can you give me the practical example of Hilbert space? Just last minute I am taking for you, because I have to finish this topic today itself here. What are the practical example of Hilbert space?
Mode of wave.
Different modes. Modes of wave. You have fundamental mode, something like this. You have first overtone, something like this. All are examples of Hilbert space. Now you can see the wave is moving only in x direction. But how many possible modes you have? You have infinite number of possible modes. And in the Hilbert space, you can treat all these modes for a wave as a independent directions. And yes, they are orthogonal in nature also. So why you can treat as unit vector I cap, unit vector j cap, and k cap, and so on. Anyway, so we will continue our discussion into next class. So tomorrow we will go for the operators and methods. Okay. So 2 class will be there for tools. Then we will go for the postulates. Maybe 1 or 2. Let's see. Okay. Thank you.
Thank you, sir.
Thank
Thank
you,
you,
sir.
sir.